Hi students, welcome to the next lecture of Electronic Measurements and Instrumentation. My name is TSS Nagapavan Kumar. Today we will see the concept of inductive type transducers. So this is the second part of the passive transducers. In the passive transducers we have three categories: resistive type transducers, inductive type transducers, capacitive type transducers. We have completed previous classes with resistive type transducers. We have seen potentiometer type resistive transducers. Next, we have seen resistive pressure type transducers. Next, we have seen strain gauges type of resistive transducers. Next, we have seen thermal based resistive type transducers. Thermal based resistor, thermal type resistors or thermistors are different types of resistive type transducers we have seen. Now, in this class, we will discuss inductive type transducers. Right. So, first of all, the inductive transducers may be either self-generating or passive type. So, the inductive type transducers are self-generating or passive type. There are two types of inductive transducers are available. The self-generating type. So, the first one, self-generating type, utilizes the basic electrical generator principle. It will use the basic electrical generator principle. That is, that principle is a motion between a conductor and magnetic field induces voltage in the conductor. So, here it is very simple. A motion between the conductor and magnetic field. A motion in between the conductor and magnetic field induces a voltage in the conductor. So, if you are placing a north and south poles, in between this magnetic field, if you are placing any conductor, due to this magnetic force, some EMF will be induced in that particular conductor. That is from the generator principle. So, we have seen the motor and generator principles in our lower UG level courses, that is in the subject of electrical technology, motor principle and generator principle. Now, from the generator principle, we can design this self-generating inductive type transducers. This relative motion between the field and the conductor is supplied by changes in the measured. So, whatever the conductor motions are available, based on the conductor motions, that EMF will be generated in this inductive type self-generating transducers. An inductive electromechanical transducer is a device that converts physical motion into change in the inductance. So, where the mechanical energy which is we are applying on this conductor, so due to the displacement of this conductor or due to the pressure of this conductor, we can produce different types of EMFs in that particular inductive type coils, and we can see different types of inductance properties at the output of these coils. So, this is the inductive electromechanical transducer. This type of transducer is called inductive type electromechanical transducers. Next, transducers of variable inductance type work upon the following principles. So, based on the inductance variations, we have two types of circuits are available. So, the first one, variation of self-inductance, variation of mutual inductance. Variation of self-inductance means we have an inductive coil. In that inductive coil, we have a conductor. We are moving that conductor and we can observe different types of EMFs. Next, variation of mutual inductance. In this mutual inductance, we have primary windings and secondary inductive windings. So, primary inductive type windings, secondary inductive windings are available. So, these are the mutual type of inductive coils. At that place, we are moving this conductor. At that time, some EMF will be generated. That is called mutual inductance property. Based on these two principles, inductive type transducers are available. Inductive transducers are mainly used for the measurement of displacement. So, the major focus of this inductive type transducers and capacitive type transducers, we are measuring the displacement. How much displacement will be move this conductor at the input side. So that the displacement parameter we are taking as the input parameter for the transducer, and output is that related, that proportional voltage, displacement proportional voltage we are observing at the output side. The displacement to be measured is arranged to cause variation in any of three variables. So that is based on the number of terms, that is geometric configuration, and third one, permeability of the magnetic material or magnetic circuits. That means when you are placing a lot of turns in the inductor, so how much turns this conductor is covering, that is we are going to identify. For example, see here, we have a conductor here. Here we have a inductive type transducer. In this inductive type transducer, I have placed a number of turns. Now, I have inserted a rod. I have inserted a rod here. Okay, this rod I have inserted. Right. Now, how many number of turns are covered by this rod? That we have to identify. That is the first principle. Number of turns. Number of turns, how many completed by using this conductor. Next, geometric configuration. Next, magnetic circuits. So these are the three types of variables we are going to be measured. So the number of turns are going to be vary here. The geometric configuration is going to be vary here, and the magnetic circuit is going to be vary here. That we will identify in this inductive type. Transducers. See here, for example, let us consider in this case a general inductive transducer, a normal inductive transducer I am taking here. The inductive transducer has n turns. The inductive transducer has n turns. Capital N number of turns is available, and a reluctance called L. We have a reluctance called L. When a current I is passed through it, then the flux is. So, in an inductor coil, we have number of turns is capital N, and reluctance is R, and current is I, is passed through that coil. Then the output, the EMF, the flux is, we are defining like this. Phi is equal to Ni by R. Phi is nothing but as flux, that is EMF, that is equal to Ni by R. Number of turns, N, I is current, and R is the reluctance. This is where we are differentiating here. d phi by dt is equal to d phi by dt. That is where we have applied the derivatives here. d phi by dt is equal to n by 2, where n is the number of turns constant, and 2 is also constant parameter, n by 2 into di by dt. That is here I am doing the differentiation for I, di by dt. Minus Ni by R square into dr by dt. Here for R and I, for these two parameters I am doing the differentiation. Okay, right. If the current is varies very rapidly, varies rapidly, you can call d phi by dt is equal to n by 2 into di by dt. Right. So here we have removed that R parameter. If the current is moved rapidly, right, we can neglect that R parameter. But EMF induced in the coil is given by E is equal to N into d phi by dt, where small e, the induced EMF small e in the coil, E is equal to capital N into N by 2 into di by dt, that is equal to N square by R into di by dt. Also the self inductance is given. Capital L is equal to the induced EMF E by the differentiation of the current di by dt. The rate of change of the current di by dt is equal to N square by R. Therefore, the output from an inductive transducer can be in the form of either change in the voltage or change of inductance. So, the transducer EMF is completely dependent upon the change of the voltage or change of the inductance. So this is a basic property and behavior of this inductive type transducer. Let us see. Here we have linear and rotational displacement. In the potentiometer, we have seen two types of potentiometer: linear potentiometer, rotational potentiometer. In the same way, here also we have linear inductive type transducer. This is the linear inductive type transducer. Here I have placed an inductor. One side I am giving the power supply, another side I am taking the output. This output terminals, one side of the output terminal I have taken this yet, and another side of this output terminal I have taken for any number of turns. Maybe I will cover with the 5 number of turns, or 10 number of turns, or 100 number of turns. Based on the selection of number of turns, I will get some different types of EMFs at the output side. So this is the linear displacement. This output terminal, I am moving linearly either upward direction or downward direction. This is the linear displacement measurement. And see here, this is the second one, angular or rotational, angular inductive type transducer. This is generally where ferrite core, for this we are taking the ferrite core. So see here, we have placed an inductor towards this coil in the conductor. So this conductor is in the form of circle type. In this circle type conductor, I have placed the terms, right? So these are the two. This is one side I am giving the power supply, and then these two terminals I am taking the output. So one terminal I have connected one end, and another terminal I am placing any of these middle coils, middle terms. So this is called rotational or angular inductive type transducer. Okay, one side linear, that is moving in the upward or downward direction, and second one is angular, it may be in the rotational point of the directions. These are the two types of potentiometers which is covering the turns. Next, variable reluctance type transducer. A transducer of the variable type consisting of a coil wound on a ferromagnetic core, that is just we have seen in the angular measurement type. The displacement which is to be measured is applied to a ferromagnetic target. The target does not have any physical contact with the core on which is mounted. The core and the target are separated by an air gap. So see here. Here I have placed a target iron rod here, and here I have placed one more type of target like C type core. This is called ferromagnetic core. You can see the ferromagnetic core. Here I am highlighting. So see here I am highlighting that ferromagnetic core. So this is a ferromagnetic core, right? So for this ferromagnetic core, the coils are turns here, right? The output, these are the output turns. Here I have placed a target iron. This is a iron based target. This is a iron based target. Okay. Here, here this iron target is moving upward and downward direction. If it is moves in the downward direction, very close to this ferromagnet, the air gap in between these two conductors are very close, then I will get high amount of output voltage at this turns. If the iron rod is moving into the upward direction, the air gap is going to be very high at this place, then there is no passes of current through this coil, then there is no output voltage. So this is a variable reluctance type transducer. In this concept, there is no direct contact of this iron rod to this coil. There must be some air gap in between this iron rod and this type of transducer, that is inductive type of ferrite core, okay, ferromagnetic core. There are two types of attachments are available. Okay, so if air gap is heavy, there is no EMF at the output side. If the air gap is very less, then some output voltage will be available at the output terminals of this variable reluctance type transducer. Okay, so the same information we have represented with the equations here. The reluctance of the magnetic path is determined by the size of the air gap. The inductance of the coil is depends upon the reluctance of the magnetic circuit. The self-inductance of the coil we are taking with this functionality, where L is equal to the self-inductance of the coil capital L is equal to N square by Ri plus Rg. Here I have used two conductors. So N by Ri plus 1 by n by Rg. That is by representing Ra n square by Ra plus Rg, where n is the total number of turns, Ra is the reluctance of iron parts, and Rg is the reluctance of air gap. So the air gap reluctance I am taking, and the iron rod reluctance also I am taking. Ra and Rg both I have taken here. So the number of turns I have taken in the form of n square. Okay. We know that the L is equal to n square by R. That is we have derived in the previous slides. So that is the expression I have taken here directly. The reluctance of the iron part, is completely negligible. That means we can cancel this Ra value. Finally, we are representing with this air gap reluctance parameters only. L is equal to n square by Rg. But the reluctance air gap is given, Rg is equal to, so the air gap reluctance we are taking as Rg is equal to Lg by mu naught into Ag, where Lg is equal to length of the air gap, Ag is equal to air of the flux path through the air, and mu naught is the permeability. So this is the Rg reluctance parameter representations. So here we are taking the air medium as the reluctance parameter. So for that reason, these are the very important. Rg is proportional to the Lg. So here we can see the directly proportional relation here. And mu naught and Ag are the constants. So this mu naught and Ag, area and permeability are both are the constants here. Hence L is proportional to the 1 by Lg. L is directly proportional to the 1 by Lg. That is the self-inductance of the coil is inversely proportional to the length of the air gap. That is the relationship between L and the remaining parameters of this reluctance Rg parameters, that is area and mu and length. Okay, so this is about the parameters. Next, when the target is very near to the core, the length is small and the self-inductance is very large. So previously I said that when the iron rod is moving to this coil, the air gap is very less, then it will produce maximum inductance. If the air gap is very large, then there is no output voltage. But when the target is away from the core, the reluctance is large. If the reluctance is very large, automatically we will get less amount of voltages at the output side. Otherwise, if the reluctance is very less, then we will get the maximum EMF at the output side. Is large, resulting in a smaller self-conductance value. It's very important. Self-conductance. Right. Self-conductance is large when it is nearer to the core. The self-inductance is very small when it is very far, when it is away from the core. From the core to iron rod is away, it is very far, then the self-inductance is small. When it is very close, the self-inductance is very high. Hence, the inductance of this coil is a function of the distance. So finally, the function of the distance, here it is a function of the distance. The inductance, the self-inductance output is completely is a function of the distance of the target from the core, that is length of the air gap. So the distance we are calling as the length of the air gap. Air gap length we can call. Right. Next. So this is about the inductive type transducers. Next, displacement differential output transducers. Here in the previous side, in the previous concept, we have only one output. But now we will see two different types of output. That is differential output transducer. Two different types of output are available. What is the differential types of output transducer? So see here, here I have taken two windings. So from this is a one point. This is the first point. Right. So see here, first, second, third. I have three output terminals. The first two terminals output is representing this L1. The second two outputs are representing L2. Now I am moving this middle point to upward direction. That means here, if the point here, this output terminal is moving in the upward direction, number of turns are less. in the L1 side and the number of turns are more at the L2 side. When the center output terminal is moving to the upward direction, the number of turns are reduced at the L1 side, number of turns are more at the L2 side. When this rod is moving in the upward direction, that is the displacement of the output terminal in the upward direction. If it is the downward direction, number of turns are less in the L2 direction, number of turns are high at the L1 direction. That is completely based on our requirement. So the displacement of the output rod is moving the upward direction or the downward direction, then the windings are going to be less and high with inversely proportional to the displacement of that rod. In the same way, here also you can observe that L1 winding and L2 windings. So one terminal is the output L1 side and the terminal is L2 side. So the middle terminal, based on its position, it will divides the flux production at the L1 side and L2 side differently. If you are placing exactly center, the two output windings, here we have two same output voltages. At the L1 side, how much voltage is there? The L2 side also same voltage we can observe at this situation. Okay, so this is linear, this is angular. Both are inductive type transducers, but we have two differential output voltages. Normally, the change in the self-inductance, that is delta L, for inductive transducers is not sufficient for detection of subsequent stages of instrumentation system. In the instrumentation system, with the one stage of del L, it is not sufficient. We have to take some other parameters also. However, it is successive stages in the instrument respond del L or del M rather than L plus del L or M plus delta M. The sensitivity and accuracy will be much higher. So the sensitivity and accuracy we have to produce very high. So for that reason we are using differential inductive type transducers. The transducers can be designed to provide two outputs, one which represent to inductance and other it will give the decrease of the inductance. So one side you have to provide self or mutual inductance, otherwise other side also you are giving self or mutual inductance. If one side inductance will be rising, other output side you will get less inductance. Otherwise other side you are increasing the inductance, the another side you will reduce the inductance parameter. That is two differential type outputs you are giving. The successive stages of the instrumentation system measure the differences between these outputs. This is known as differential output. So this is the mechanism called differential output behavior. Right. So what is the advantage by getting two outputs? What is our advantage by getting two outputs for the number of stages? Sensitivity and accuracy is increased 100%. So total flux we can see in the two outputs. Okay, if once for example you are getting 50 volts at the output side, so at the two generally when you are displacing the conductor, one side you will get 20 volts. The remaining 30 volts we are getting or not we can observe at the second output side. So by combining these two voltages you will get the exact output voltage. With this you can identify how much output voltage is generating and how much output voltage is not generating. That you can identify easily. Output is less affected by the external magnetic fields. With the external magnets we can avoid the other effects also. Effective variations due to temperature changes are reduced. So the temperature variations are also going to be reduced here. Effects of supply in voltages and frequency are reduced. So supply voltages or frequencies also we can reduce. Right. In the next class we will see the concept of LVDT principle. With this we have completed inductive type transducers. LVDT also one type of inductive type transducer. This concept we will see in the next lecture.